Good morning. Today we are going to discuss the motion of this pendulum and ultimately simple harmonic motion. So let's commence operations. So our primary objective is to understand simple harmonic motion. Secondary objective is to investigate the relationship between the position time, velocity time, and acceleration time graphs for a pendulum. Specifically, we'll be looking at these two equations. And we'll show that these two equations for position and velocity accurately model the movement of the pendulum. We will also verify these two equations through measurements. Specifically, we will be verifying that equation that I've circled for the amplitude of the velocity. And we will also explore what this formula means in terms of the acceleration of the pendulum. Our final objective will be to understand how the motion sensor creates the graph in real time. There's a hint. Sound is involved. And so, our primary objective, to study simple harmonic motion. This graph represents simple harmonic motion. To understand this graph, we will look at the position of the pendulum at different points in time. This is one extreme position of the pendulum. Here we have the middle position of the pendulum. And finally, we have another extreme position for the pendulum. And then, of course, the pendulum goes back and forth. The middle position is called the equilibrium. And so where is the equilibrium in this graph? Well, it's right over there. And I've denoted that with that circle there. In fact, notice there are several times that the graph shows the equilibrium position. And that is, of course, because the pendulum goes back and forth. All right, now let's look at the pendulum moving towards the right. Eventually hits that extreme position. That extreme position is that point of the graph. Notice it's reading around 40 centimeters, 0.40 meters. That's basically saying that that specific position, it is around 40 centimeters or 0.40 meters away from the motion sensor. Now, after hitting its maximum position, it starts to move back towards equilibrium. And it passes through equilibrium again, and this is shown there. It continues moving, and then hits another extreme position. That's shown there. And now it turns around. Goes back to equilibrium, and that's represented by that specific point on the graph there. This represents one cycle of motion. Notice I have highlighted 4 cycles of motion. Now 4 cycles of motion seems to be around 7.6 seconds. Notice that cycle starts at around 11 and it ends beyond 18, somewhere between 18 and 19 seconds, and that's around 18.6 seconds. And so if 4 cycles of motion is 7.6 seconds, then 1 cycle of motion is around 1.9 seconds. The time to complete 1 cycle of motion is called the period. That's represented with the symbol capital T, and that's 1.9 seconds. Notice that simple harmonic motion is repetitive. It repeats. In addition, notice that the period does not change. It remains consistent. It's always 1.9 seconds. The formula for frequency, it's 1 over the period. And so since the period is constant, then the frequency also does not change. So simple harmonic motion is motion consisting of a single frequency. And in physics, we often call a single frequency a harmonic. Hence the term simple harmonic motion. Our secondary objective is to investigate the relationship between the position time, velocity time, and acceleration time graphs. Is there an equation that models simple harmonic motion? Well, there is. And it's given by this equation here. X represents the position of the pendulum. X0 represents the maximum displacement from the equilibrium position. It's shown there in the graph. Notice, however, that as we move on in time, X0 decreases slightly. Eventually it'll be 0 when the pendulum comes to a complete stop. So this formula is only an approximation for the motion of a pendulum as the amplitude decreases due to energy loss. However, this is the formula used to represent simple harmonic motion. Sometimes you may also see a cosine instead of a sine. You will see the cosine if at time 0 the graph starts at a maximum position, as you see here with the graph. Well, we're going to stick with the sine representation, and now we're going to explore what that symbol means, omega. Omega is called the angular frequency. It's represented by the expression 2 pi over the period. And that can be rewritten like that, or sometimes you can see it written like this. So what about a formula for velocity? So in a moment, I'm going to ask you to focus on the velocity time graph. Let's see. So here's the velocity time graph created by the motion sensor. And I want to now focus on these two graphs at the same time. Notice that there seems to be an offset or a shift in the graph. Actually, in physics we say that these two graphs are out of phase by 90 degrees. So what does positive velocity mean? Notice we have a positive velocity of around 0.4 meters per second. Well, when that positive velocity of 0.4 meters per second is achieved, it seems to be achieved at the equilibrium position. And so positive velocity means the pendulum is moving away from the sensor. Now it's fastest at equilibrium since it's at its lowest point. Remember, at its lowest point it has the least potential energy, therefore the greatest kinetic energy. So what does negative velocity mean? Notice negative velocity has occurred at that point. It's around negative 0.4 meters per second. And once again, it seems to line up with the equilibrium position. Negative velocity means the pendulum is moving towards the sensor. And so notice there are many points when the velocity is 0. Let's look at one point there. Notice that the velocity is 0 when it seems that the pendulum is closest to the motion sensor. So write this position here. Well, remember at maximum height, the velocity is always 0. Potential energy is at a maximum, and of course, kinetic energy is 0. Let's look at the velocity there when it's 0. That seems to be when the pendulum is at a maximum point, when it's furthest away from the sensor. And so at maximum height, once again, the velocity is 0. All right, so we have our position, our velocity time graphs, and there is our equation for the velocity. So how do we know this is correct? Specifically, how do we know that the amplitude is given by that expression, omega multiplied by the amplitude of the position time graph? Well, we're going to verify this with data from the VT and DT graphs. Recall, omega is 2 pi over the period. So we could substitute that. And we're going to evaluate this based on the data from the sensor. Once again, the period is 1.9 seconds. What about the amplitude? Well, let's solve for the amplitude using the position time graph. Notice I have drawn an arrow, and that arrow represents 2 times the amplitude. Well, the peak height of the position time graph seems to be at around 0.40 meters. That's this position here when it's 0.40 meters away from the sensor. And it seems to hit a point somewhere between 15 and 16 centimeters. We'll call it 16 centimeters. And so at that specific position, the pendulum is 0.16 meters away from the sensor. Solving for double the amplitude by taking a difference of those two numbers and working through the math, it turns out the amplitude is around 12 centimeters or 0.12 meters. And so working through this expression, substituting the period of 1.9, substituting the amplitude of 0.12 meters, we end up with 0.397 meters per second. Interesting. Now with significant digits, I think the best we can say is 0.40 meters per second. Substituting that expression, we end up with this expression for the velocity. Does the velocity data from the sensor confirm this? Well, let's take a look. Let's see. And it does. Notice that the peak amplitude of the velocity time graph, according to the information we got from the motion sensor, is around 0.4 and negative 0.4. So through the position time graph and the velocity time graph, we have verified that this expression is correct for the velocity. Now, is there a math connection between these two expressions? There is. To study that math connection, we have to study calculus and use something called a derivative. That's not the purpose of this video today. What about acceleration? Well, this is the expression we have for acceleration. Negative omega squared times the position. And so substituting, we end up with this expression for the acceleration. Again, those two expressions are connected with a derivative. Today we're going to focus on the negative. What does the negative imply? And so let's go back to our position time graph. And let's try to sketch the acceleration time graph based on this idea of a negative. And so we have the expression a equals negative omega squared multiplied by the position. So this means that when the position is positive, the acceleration is negative. That's what a negative means. And when the position is negative, a negative of a negative means the acceleration is positive. And so we end up getting graphs that look like this. We say that when we have two graphs with this type of relationship, that they are 180 degrees out of phase. Does this make sense? To explore this, we'll look at Newton's second law. Specifically, acceleration is proportional to net force. So let's examine that position there, when the pendulum is furthest away from the sensor. Well, that lines up with a negative acceleration. So examining the forces, gravity acts downwards, and tension acts along the direction of the string. Breaking tension up into its components and focusing in on the vector that's white. When the pendulum is to the right of equilibrium, the force acts towards the left. And remember, acceleration is in the same direction as the force. So yes, it makes sense that it's negative. When we're to the right, which is a positive value for position, the force acts towards the left. And now let's examine another point of interest. Let's examine when the position is 0. Well, according to this relationship, the acceleration is also 0. At equilibrium, the acceleration is 0 in the direction of motion. So examining the forces once again, gravity acts downwards and tension acts upwards. Notice there are no forces acting left or right. And so because there are no forces acting left or right, then the acceleration is 0 in the left or right direction. And so indeed, this idea that acceleration is the negative of position seems to make sense. Our final objective is to understand how the motion sensor creates the graph in real time. And so let's focus in on the position time graph. And let's look at that point there. So the sensor generates a pulse of sound. The sound is incident on the pendulum. The pendulum will reflect the sound. And then the sensor will detect the sound that is reflected. Now the computer measures the time for the pulse to travel forwards and then backwards. And it uses this equation here. Distance equals speed multiplied by the time of travel divided by 2. Now the speed is the speed of sound, which is 344 meters per second. So y divided by 2. Well, the time that's measured is the time for the sound to travel forward and then the time to travel backward. So that's why we have to divide by 2. It's effectively measuring double the time. I hope you enjoyed today's explanation of simple harmonic motion. Have a great day. Bye-bye.